Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. On the surface, cementing is just a routine part of an oil or gas well's life. In fact, primary cementing of the casing is normal practice at the drilling and completion stage of all wells. The procedure seems straightforward. Drilling is halted, and a casing string is run in the hole. A service company sets up the necessary equipment, mixes the cement slurry, and pumps it down hole. But the challenge is present below the surface, where difficult, often changing physical and chemical conditions exist. Here, cement slurry is pumped down the inside of the casing and up into the annular space between casing and the wall of the hole, or between casing and previously cemented casing strings. And here, if the casing was centered, the well bore properly prepared, the slurry well mixed, and the right additives chosen for the downhole conditions, the cement will set and form a permanent support for the casing and a barrier to fluid movement between zones.
When primary cementing is successful, it also protects the casing from corrosion, protects the casing from shock loads during deep drilling, prevents blowouts, and seals off lost circulation or underpressured zones. Primary cementing is one of 3 basic cementing procedures. The other 2, which are usually considered secondary or remedial cementing, are squeeze cementing and plugging.
Squeeze cementing is performed either to correct a poor primary cementing job or to stop unwanted fluid production caused by changing reservoir saturations or unsuccessful completion attempts. In a high-pressure squeeze, cement is pumped into the well at pressures that exceed the formation fracture pressure. This causes fractures to propagate from the well bore. These induced fractures are intended to intersect the existing fractures or voids responsible for unwanted production. The induced fractures remain full of cement after the treatment and thus block production from these areas. In practice, this method has a low success rate, probably due to the unpredictable growth of the induced fractures. A low-pressure squeeze does not exceed the formation fracture pressure, and it may only require a couple of barrels of cement as opposed to 100 barrels for a high-pressure squeeze on the same interval. During a low-pressure squeeze, filtrate from the slurry is forced into the formation flow channels, creating a buildup of cement filter cake. A properly designed slurry leaves only a small cement filter cake bump, called a node, inside the casing after excess slurry is circulated out of the well. Plugging is necessary when zones are to be isolated. Special tools are to be set in the well bore, or a well is to be abandoned. The cement plugs are set by circulating the cement through tubing or drill pipe over the desired interval. The tubing is then raised to the next interval to be cemented or removed from the well.
Your manual covers these secondary cementing procedures in much greater detail, so be sure to read it. This video program will focus exclusively on primary cementing practices. Done properly, they can save substantial costs for future remedial work.
The major cost benefits is a reduction in squeeze cementing, because cement itself is a very cheap thing to put into a well. But when you don't get a good primary cement job and you must go back to repair it, then the cost of rig time and the general remedial cementing operations mount up. So if you can eliminate your remedial cementing costs, then you can cut your overall cementing costs by more than a half.
In Unit 1, we'll describe the manufacture, chemistry, and classification of oil field cements. Since the downhole environment affects cement placement and strength, we'll consider the variety of additives available to tailor a cement slurry to suit specific well conditions. In Unit 2, we'll present basic primary cementing methods and look at the wide assortment of surface and downhole equipment. In Unit 3, we'll observe actual cementing procedures. While on location, we'll will also consider important quality control practices. Let's begin with a look at oil field cement.
Cement was first used in the oil industry in 1903. Since then, a variety of surface and downhole equipment has been developed to greatly improve the cementing process. Today, this equipment, together with specialized cements and additives, can effectively cement virtually any well. Portland cement is the kind of cement used in the oil field. Portland cement is a type of cement and not a brand name. Its manufacture has changed little over the past 160 years. First, dry carbonate and clay materials are ground to a fine consistency and passed through a kiln at temperatures between 2600 and 2800 degrees Fahrenheit, 1427 to 1538 degrees Celsius. In this temperature range, complex chemical reactions form a material called clinker. The clinker is then ground together with gypsum, producing the mixture called Portland cement. The chemical components of Portland cement are given in your manual. The amounts and fineness of the ingredients of Portland cement are modified to meet API specifications for various oil field applications. The API has 9 classifications of oil field cements based on these chemical modifications. Classes A through C are intended for wells up to 6,000 feet deep. Classes D through J are intended for deeper wells. Classes D, E, F, and J are seldom used and will soon be removed from the API specs. The hardening and strength of set cement relies on the chemical reaction of water with the components of Portland cement. Water is added to the dry ingredients and surrounds the individual particles. Gel develops around each particle of cement, and a byproduct called calcium hydroxide crystals appears. Filaments grow out of the gel, interlock, and bond all particles in the mix into a progressively hardening aggregate. Since cement hardens through chemical change and not drying out, cement will harden in air or water. API-classified cements must meet specifications for soundness, fineness, free water content, compressive strength, and thickening time. API Specification 10 and ASTM publications fully describe these properties, as well as methods for obtaining cement samples and preparing slurries. Laboratory testing is done to ensure that the properties of oil field cement conform to these specifications. Tests for soundness and fineness are done according to ASTM procedures. Soundness is determined with an autoclave, an apparatus that uses superheated steam under pressure to sterilize and dry the subject material. Fineness is tested with a turbidimeter, which measures the specific surface in square meters per kilogram. A test for free water is only necessary for Class G and H cements.
The purpose of free water control is if you have free water breakout in the slurry and your well is deviated, as virtually any well is, then the water can rise up, break out, and form a channel along the high side of the well. If it does that and can communicate between a zone of high pressure and a zone of lower pressure, then the only force holding the higher pressured zone back would be the weight of the water, which is significantly less than the weight of the cement, and it allows flow after cementing, which is one of the major difficulties in cementing.
In the test for free water, the cement slurry is stirred in a consistometer for 20 minutes, allowed to stand for a period of time, then remixed in a blender for 35 seconds, and placed in a graduated cylinder for 2 hours. Since free water volume can be significantly affected by hole angle, free water tests for deviated wells are often conducted with a graduated cylinder placed in various positions, in addition to the API-specified vertical position. The supernatant water is then measured. Its volume should be less than 3.5 milliliters per 250 milliliters of initial slurry. The API test measuring the compressive strength of a cement requires that the cement sample be prepared and allowed to cure under strict time, temperature, and pressure conditions. The compressive strength testing machine then records the hydraulic load that the cement sample can withstand before crumbling. This load is then compared with the minimum compressive strength requirements for API cements. These requirements have been determined experimentally and serve as the industry standard. The API test has its limitations. It only records compressive strength at a few specific times. On the other hand, an ultrasonic cement analyzer continuously measures the transit time of the hardening slurry and then calculates compressive strength as a nonlinear relationship with time. Though such equipment is not required for API testing, it provides information about slurry setting properties that may prove useful under certain conditions. Thickening time tests measure the length of time that a cement slurry remains in a pumpable fluid state. These tests are conducted under laboratory conditions specified by the API. A pressurized consistometer equipped with a heating element is used to simulate well conditions. The pressure and temperature are increased according to specification schedules.
Even though cement quality can be assured, a slurry made from one of the 9 kinds of Portland cement may still not suit specific well conditions. In fact, such neat slurries, having no additives, have properties that limit their use in most wells. Additives can be used to modify slurry properties to produce a tailored slurry suitable for specific conditions.
With tremendous differences among wells, from the extremes of pressure, temperature, and depth, to the drastic variations in formation stability and produced fluid chemistry, additives are the only way cement can meet all the demands. Additives help with both slurry placement and long-term cement competence. Additives are commonly used to alter properties of the cement slurry, such as thickening time, density, rheology, fluid loss characteristics, and lost circulation tendencies, and modify properties of the set cement, such as compressive strength, strength retrogressions, strength loss with time, and expansion or contraction. A widely used additive called an accelerator speeds up cement thickening time and increases the early strength of the slurry. This is often desirable for quick jobs such as surface pipe, long strings in shallow wells, and setting plugs. Accelerators can sometimes compensate for the slowdown in setting caused by other additives. Cement retarding additives slow down cement thickening time in order to provide enough time for placement of the slurry. This is often desirable in deep and hot wells. Some common retardants are lignosulfonates, organic acids, CMHEC, and modified lignosulfonates. Extenders such as bentonite, pozzolan, diatomaceous earth, and anhydrous sodium metasilicate are additives that reduce slurry density. This is done to avoid damaging weak formations and risking lost circulation. Although cement strength is reduced to some degree, it usually remains sufficient to be functional. Alternatively, hollow spheres have proven effective in providing a strong, low-density cement for use in underpressured wells, hot geothermal wells, and other special applications. An increase in slurry density may be necessary in order to control high-pressure wells or to prevent the deterioration of fragile well bores. Weighting agents in the form of either heavy materials or dispersants can accomplish this. Sand, barite, hematite, ilmenite, and salt are heavy materials that create greater slurry density because of their high specific gravity. This table lists the specific gravities of these materials and the maximum slurry densities obtainable. Caution should be taken with salt and barite, since they can sometimes reduce the compressive strength of set cement to unacceptable levels. Dispersants increase density by reducing the amount of water in the slurry. They permit the cement slurry to remain pumpable, even with these lower water ratios, and help maintain turbulent flow at all pumping rates. Turbulence is essential in removing mud, a necessity for good cementing. Common dispersants are lignosulfonate, organic acids, and certain polymers. In addition to increasing the density of the cement, dispersants can also serve to reduce fluid loss. Fluid loss is a potential problem for any cementing job. Fluid loss is the undesirable transfer of mix water from the slurry into adjacent zones before the cement hardens. This occurs in permeable zones where pressure on the slurry acts to filter out water. Fluid loss causes a change in slurry chemistry and can lead to incomplete hydration and possible cement failure. Fluid loss can also result in a decrease in slurry volume, with the danger of insufficient cement fill-up in the annular space. Fluid loss can be controlled with additives such as organic polymers, which form micelles or films that contain the liquids within the slurry. and latex, which forms a film that causes the slurry materials to adhere to one another. The goal of fluid loss control is to keep that fluid loss to less than 100 milliliters.
Chevron believes in controlling the filtration rate on its primary production cement jobs to less than 100 mils in the standard API 30-minute test and to less than 50 mils in a liner test, because empirically they found that those results give them the best primary cementing success ratio. In other words, the least amount of remedial work.
If you keep the filtrate water coming out, that's trying to come out of the cement below 100 cc's, then you're ensuring that there's plenty of water present for the cement to react with, as well as you're not losing your water to the formation, which can cause damage to the formation.
Occasionally, the entire slurry seeps into thief zones, or natural fractures, and mud stops returning to the surface, indicating that circulation has ceased. This lost circulation generally requires the additional expense of remedial perforation and cementation in order to finish filling the annular space. Lost circulation can be controlled with materials that obstruct flow into fractures or seal off fragile zones as the cement is being placed. Materials that accomplish this are granular materials, such as walnut shells, gilsonite, and perlite, which plug or bridge off the lost circulation zone, and laminated materials, such as cellophane flakes, which form mats against the porous formation. Fibrous materials, such as nylon, are no longer used because they tend to plug surface and downhole equipment.
It is important to remember a couple of things regarding additives. They should be used only when absolutely necessary, since they increase cost and complicate slurry chemistry and properties, and they should be field blend tested.
Field blending tests or field blend tests are very important because you need to assure that you will get the properties that have been designed into the laboratory. Even if you've isolated the cement and you've isolated the additives for a particular set of tests, it's still possible that there were errors in the scales, for example, or contamination from a transport vehicle, which would still give you disastrous results on site.
The field blend testing of additives and cements and the API testing of cements are an integral part of the larger quality assurance picture. Such practices are essential to the success of a cementing operation.
What constitutes a good quality assurance program is generally decided by the production companies. What we do as far as quality control is ensure that the cement itself is adequate and meets API specifications. The additives that we're putting in there is QC checked to make sure that they fall within our design criteria.
Chevron's developed a quality assurance program that involves the design of the slurry itself, cooperatively testing that slurry with the service company lab, because that provides a cross-check with both laboratories, and then on-site blending supervision or supervision at the bulk plant, testing of those blends, and then on-site supervision of the actual job itself.
You'll find more information on cements and additives in your manual, so be sure to read it. At this point, please stop the tape, read Unit 1 in your manual, and do the assigned exercises. We have seen that for a cementing operation to be successful, the cement and additives must be carefully designed and QC tested. Next, they've got to be thoroughly mixed and delivered down whole. What's involved?
Other pre-job planning besides quality control involves deciding on which cementers are going to do the job, which pump trucks are going to come out to location, what cementing heads, plugs are necessary, what type of equipment is going to be used, or batch mix job, jet mix job, or recirculating mixer type job.
And then there are questions about effective placement of cement over the required intervals and secure bonding of the cement to the formation, like how are widely spaced intervals cemented, given that fragile zones are apt to crumble under the weight of a long column of cement, and how can cement bond firmly when there's drilling mud and mud cake in the hole? We'll answer these questions in this unit, which presents the equipment and procedures used in mixing, placing, and bonding cement. Let's begin by considering the basic primary cementing methods.
Primary cementing is performed as either a single-stage or a multi-stage operation. The single-stage method is used whenever a continuous column of cement is to be placed in the annulus. It requires that all exposed formations be able to support the hydrostatic head of the cement slurry. The most common single-stage operation uses two rubber wiper plugs. Here, a hollow wiper plug, temporarily sealed with a thin membrane, enters the wellbore. A cement slurry is pumped behind the plug and pushes it down whole. The plug wipes debris from within the casing and acts as a barrier to prevent the drilling mud from contaminating the cement. A solid wiper plug enters the wellbore immediately behind the cement slurry. Displacement fluid is pumped behind this plug and pushes it down the well. The plug clears all cement from inside the casing and also prevents the displacement fluid from contaminating the slurry. The hollow plug seats in equipment at the bottom of the pipe. Continued pumping ruptures the thin membrane so that cement can flow through the collar and up into the annulus. And then the solid plug seats and blocks further movement of fluids, preventing both over-displacement of cement and backflow of cement into the casing. Single-stage procedures have been performed using only one or even no wiper plug, but this is strongly discouraged because it can lead to contamination of the cement and the inside of the casing. Now let's look at conditions that require multi-stage treatments.
Multi-stage cementing is done when you have a low-pressure zone that will possibly break down due to the hydrostatic head of the cement.
The other reason would be pay zones that are separated quite widely in the well. In other words, a pay near the bottom and then another pay maybe several thousand feet up the hole. Maybe it's a secondary pay zone, and you want to cover it with good production cement, but you don't want to use production cement for the entire well.
In both these cases, the multi-stage cementing of two or more separate sections behind the casing provides a cost-effective alternative to single-stage treatments that reduces the volume of cement required and removes the danger of incomplete and unsuccessful cementing. In preparation for multi-stage cementing, the normal single-stage tools are assembled. Then stage cementing tools are installed in the casing string as it is being run. These tools are placed wherever cement is to be pumped behind the casing. Each tool is designed to be selectively opened by a specially sized free-fall plug. When the casing is on bottom, cement is placed over the lowest zone using the same procedures required for single-stage cementing. Then a free-fall plug enters the wellbore and triggers the opening of a port in the lowest stage cementing tool. Fluid is circulated for a brief period to clean and condition the borehole. And then enough cement is pumped to fill the second stage. A wiper plug enters the wellbore behind the slurry. All the cement passes through the stage cementing tool, and the plug activates the closing of the circulating port, preventing cement backflow into the casing. Subsequent uphole intervals are stage cemented in the same manner, using free-fall plugs respectively sized for each stage cementing tool.
All primary cementing jobs include other downhole and surface equipment. The downhole equipment is run along with the casing and cemented in place. The most common examples are guide shoes, float collars, centralizers, agitators, scratchers, and cement baskets. The surface equipment is basically the same for single or multi-stage techniques and typically consists of bulk cement transports, mixers, pumping units, and a cementing head. Let's begin by considering how cement is delivered to the job site.
To minimize mixing time on location, the service company normally prepares the dry bulk cement mixture at its bulk cement plant. The company engineer will have inspected the bulk cement plant well in advance of the job to ensure that conditions are sanitary and that accurate methods are available to blend the mixtures. Since precision is crucial when weighing and mixing cement and additives, it is essential that equipment be certified accurate. A bulk cement facility that uses state-of-the-art weighing equipment is best. The dry ingredients are placed in a batch blender and mixed pneumatically. The company engineer routinely requests a copy of the bulk plant load sheet to confirm what dry additives were used. The load sheet is retained in the permanent well file. The dry ingredients are then loaded into bulk cement transports. These trucks will carry the bulk cement to the location. A compressor on the transport pressurizes the cement storage bins, enabling them to be placed in any position without the need to depend on gravity feed. Most cement transports have storage bins that are vertical cylinders with domed heads and conical bottoms. When the job begins, the pressure in the bins will force the dry ingredients into discharge pipes that lead to the mixer.
When choosing the type of mixing equipment to use, if conditions allow, the batch mixer is always the best way to go because it assures that your density is dead on perfect.
With a recirculating mixer, which is second best, you can get it to within 0.2 of a pound per gallon. And with the jet mixer, you can get it about a half pound per gallon.
A recirculating mixer is the most common type of mixer used on primary cementing jobs. This type has replaced the older model jet mixer because of its improved uniformity of slurry and its ability to operate efficiently with slurry densities as high as 22 pounds per gallon. The mixer proportions and blends dry cement ingredients with fresh water. Of the several designs of recirculating mixer, this one has a valve on top which controls the rate at which the dry ingredients enter the mixer. Nearby, a mixing manifold controls the rate of the water. The partially mixed bulk cement and water discharge into the pre-mix side of the mixing tub. Here, turbine agitators further blend the mixture into a slurry. Centrifugal pumps draw part of the slurry from the bottom of the tank and feed it through lines to a densimeter. The densimeter measures the slurry density and displays it as a digital readout. If necessary, the operator readjusts the bulk cement-water mixture to conform to design specs. The tested slurry then leaves the densimeter, combines with more bulk cement and water, and recirculates to the premix side. When the premix side of the mixing tub is full, the slurry flows over a weir, helping to remove entrapped air, and then spills into the downhole side of the tub. This second compartment holds slurry at the correct density. An agitator continuously blends new slurry with the contents of the compartment to ensure a uniform mixture. Triplex pumps draw this homogeneous mixture from the bottom of the compartment and pump it toward the well. Triplex pumps are positive displacement single-acting pumps that are powered by a diesel engine rated at several hundred horsepower. Due to a wide range of operating conditions, the pumps and powertrain are designed for maximum rather than average pressures. Cement travels from the discharge side of the pump through high-pressure lines leading to a cementing head. A cementing head is specially installed for the cementing operation. It enables connection of the high-pressure lines to the casing for delivery of cement downhole, and serves as a receptacle for the wiper plugs. A cementing head normally holds 2 wiper plugs. It is designed so that the plugs can be released from the container without interrupting pumping. When the pre-flush volume has been pumped, a worker shuts off the lower valve, releases the bottom pin, and opens the middle valve. Cement is directed down on the hollow plug, forcing it out of the head and into the casing. When all the cement has been pumped, the worker closes the valve, releases the upper pin, and opens the top valve. Displacement fluid forces the solid plug into the casing. It is critical, when 2 plugs are used, that the hollow plug is in the bottom position in the cementing head. Otherwise, the solid plug will seat downhole ahead of the cement, circulation will cease, and the casing will end up full of cement, necessitating costly remedial work. Wiper plugs are designed to seat in either a guide shoe or a flotation device. A guide shoe, normally a round-nosed steel device, is installed at the bottom of the first joint of casing. During running, its shape helps direct or guide the casing through hard shoulders and deviated holes and away from ledges. The guide shoe provides relatively smooth passage through the wellbore, eliminating the tendency to get hung up and the danger of caving. Guide shoes are routinely run on all casing strings. A special type of guide shoe, called a Texas pattern shoe, is designed with a beveled edge, which enables the casing to rotate and chisel through ledges. This type of shoe is run in shallow wells, where hard ledges may be encountered that would cause a round-nosed shoe to simply spin on the ledge. Often, the Texas pattern shoe is notched to give better drilling action when passing through a ledge. When casing is being run, the weight of the suspended pipe can be a considerable strain on the derrick. A degree of casing flotation is therefore desirable in minimizing such stresses. Flotation equipment accomplishes this by sealing the casing near the bottom. The upward force of the drilling fluid, thus prevented from flowing into the casing, acts to buoy the casing and support a portion of the casing weight. As the casing descends, the buoyant force tends to slow the downward travel of the string. Eventually, it would completely stop the pipe from continuing downhole. To prevent this, where a float collar is the flotation device of choice, running is halted periodically and drilling mud is added from the surface to the inside of the pipe. The additional weight of the mud allows the string to continue moving down the hole. An automatic fill-up collar provides an alternative method that eliminates the frequent stops necessary to fill the pipe with mud. The auto fill-up collar is run into the hole with a lower sliding sleeve closed against the bottom valve. Pressure builds from below, forcing the sleeve up and allowing fluid to flow around the flapper and up into the casing. When the force ultimately shifts down on the sleeve, it closes against the flapper and stops flow. With the casing a few joints off bottom, a ball is dropped through the pipe and seats on the upper sleeve. Pressure is applied from above to shear retaining screws. The sleeve slides down. The spring-loaded flapper valve snaps shut, and flotation is achieved. An insert flapper valve is another kind of auto fill-up flotation device. Made of aluminum, it has a spring-loaded cast iron flapper on the bottom with a rubber seal around the edge. During assembly, a phenolic sleeve with a carefully calculated orifice is inserted. It holds the flapper open and allows a regulated flow of drilling fluid into the pipe as it is run. The sleeve is held in place by a split ring. As the casing nears bottom, a weighted plastic ball is dropped through the pipe and seats on top of the orifice tube. When the casing reaches the setting depth, pressure is applied against the ball, causing the orifice tube to shear off at its top edge and be forced down and out of the valve body. The flapper valve springs shut and remains shut due to the greater pressure from below, and flotation is achieved. Float collars and automatic fill-up collars are usually positioned 1 or 2 joints above the guide shoe. This provides a space between the seated wiper plugs and the shoe where debris can collect and remain in the casing, and not in the annulus. This helps ensure that the quality of the job will not be compromised by contamination of the cement. Since holes are rarely drilled perfectly straight, the casing, when on the bottom, will have a normal tendency to contact the wall of the hole across various intervals. Such situations can result in cement channeling and incomplete cement placement. Both can jeopardize the success of a cement job and necessitate costly remedial work. Casing that is centered in the wellbore enables cement to be placed most effectively. Casing centralizers are installed over casing collars as they are run and keep the pipe centered in the hole. In addition, centralizers reduce drag and minimize sticking as the pipe is run. Universal acceptance of centralizers, though, is not yet 100%.
Even though centralizers have been shown to be beneficial in a primary cement job by aiding mud displacement, there's a reluctance on the part of some supervisors to run them because it's perceived that by putting a whole lot of jewelry on the pipe, it's going to make it harder to get to bottom. When in fact, once you get past the initial resistance, it's been demonstrated that centralizers can actually help you get to bottom.
The spring bow type of centralizer design is used almost exclusively. Its heat-treated steel springs provide a centering force in all directions and compensate for a wide range of hole irregularities. A new design in spring bow type facilitates shipping and handling. These centralizers have several hinged sections that enable flat storage. Tests have indicated that they are just as strong as the earlier types. Centralizer spacing is based on either the manufacturer's published recommendations or load deflection curves.
Poorly centralized casing does not automatically result in a failed cement job. Tests have shown that cement with channels and voids is often capable of adequately supporting the casing. In fact, such jobs are usually considered acceptable provided unwanted fluid movement through these channels is not an issue. In cases where fluid is able to travel through these channels, problems can occur. The danger is that vertical flow through these channels can provide an undesirable link between zones. This can result in the invasion of fluids, like water, into a producing interval or cause the failure of future stimulation attempts. Thus, in areas where annular flow must be eliminated, acceptable cementing is not enough. Good cementing is a must. No channels and no voids. Cement that supports the casing and prevents fluid movement. And good jobs require not only centralized casing, but good bonding, meaning the cement to the formation. And that means removing the drilling mud.
One of the most important factors in a primary cement job is removal of the drilling mud. Because even if you design a good, competent cement slurry with all of the anti-flow after cementing properties and all the good compressive strength development, if you can't remove the drilling mud, then it can't do its job.
Scratchers, like centralizers, are run on the casing across from intervals where a good cement job is especially important. All scratchers are constructed of either rigid wire or steel cable and are welded or clamped to the casing. Scratchers, scraped against the wall of the hole in either a rotating or reciprocating pattern, remove mud cake from the borehole and enable the cement to bond firmly to the formation rock. The rigid wire type of rotating scratcher is made of high-strength steel wires with angled ends that cut and remove the mud cake. The cable-type scratcher has loops of corrosion-resistant cable that remove the mud cake. The cables overlap to ensure abrasion over the entire interval. Cable-type scratchers are considered stronger and more durable than their wire counterparts. Both kinds of rotating scratchers are used predominantly in shallow or straight holes where strain on the equipment is minimal and damage to the fragile scratchers is not a problem. In deep or deviated holes, excessive torque may be required to rotate the pipe. Under these conditions, rotating type scratchers would be damaged. In such cases, reciprocation of the casing string is the alternative method. Stronger reciprocating type scratchers are installed over critical cementing intervals and are spaced about 10 to 20 feet apart, but not exceeding pipe movement.
Since the cost difference is insignificant, selection of scratcher type and method is based on hole conditions and personal experience. However, no matter what scratcher type is used, the mud is circulated as soon as the casing is in the hole. Conditioning the mud helps to remove debris from the wellbore and results in more efficient scraping.
Before the cement job, it's important to condition your mud to premium or optimum properties because the idea is to make the mud as easy to displace from the hole as possible. This means that your yield point, which has been raised due to dehydration while you've been logging and running your casing, needs to be lowered. Your gel strengths, which also through dehydration have increased, need to be lowered. And by lowering your yield point and lowering your gel strengths, you make it easier to displace the mud. It requires less energy to push the mud from the hole.
Sometimes there is a danger that scratchers will remove both the thick gelled mud cake and the thin well-packed mud cake, with the danger of increasing fluid loss.
You don't want to remove the thin, tough filter cake that you spent all that money laying down. What you do want to remove is the gelled mud that has become thick and viscous while you're doing your logging and while you're running your casing in the hole. That mud's gelling up. That's the mud we want to remove. The thick or the thin, tough filter cake actually helps the cement job by slowing down the rate of filtration from the cement.
In these situations, agitators are often used to avoid damaging the thin mud cake. Agitators have fins that create turbulence when fluids are circulated. This results in more effective mud removal.
What agitators are intended to do is change the flow path of the cement. And wipers, cable-type wipers, are intended to break up the gelled mud. So actually the one is not a replacement for the other, but they can be used in conjunction. You use those in conjunction with pipe movement, which is the single greatest factor in a successful primary cement job. The reason for pipe movement was brought about by a study that within the company that showed that if you didn't do anything but run pipe to bottom and cement it worldwide, your success ratio was approximately 50%. If you moved casing and didn't do anything else, kept your slurries the same, then your success ratio increases to approximately 90%. And the reason for this is if you look at the wellbore in a cross section, because your casing is always going to be slightly off center, there's a wide side of the hole and there's a narrow side of the hole. It requires quite a bit more energy to move the mud out of the narrow side of the hole than it does from the wide side. So the purpose of the pipe movement is to always change that wellbore geometry so that what was the wide side at the top of the stroke might be the narrow side at the bottom of the stroke.
A cement basket is often run on the casing to shield highly permeable or weak zones from the hydrostatic head of the fluid in the casing annular space, or to prevent upper stage cement slurry from dropping through the mud. As the cement slurry passes up into the annulus, the basket's flexible steel staves expand under the weight of the cement, brace against the wellbore, and prevent cement from moving downward. Cement baskets are slipped over the casing as it is run and allowed to slide freely between collars, or they are fixed to the casing by welding or clamping.
At the beginning of this unit, we emphasize the importance of good mixing, placing, and bonding. That's because most often, cementing problems are attributed to inadequately blended slurry, poorly centralized casing, and unremoved mud and mud cake. So it's essential to know how to prevent and resolve these problems. Your manual covers this material in greater detail, as well as the equipment required for remedial cementing operations, so be sure to read it. For now, please stop the tape, read Unit 2 in your manual, and do the assigned exercises. Let's get a first-hand observation of long-string primary cementing as it's done in the field. We'll follow drilling and cementing operations being performed on wells in West Texas. These wells, drilled to around 3,500 feet, are all infill locations, so basic reservoir data is known in advance. Pre-job planning for all of these wells has followed a relatively similar pattern. Several days before reaching TD on each well, the engineer knows the approximate hole conditions, such as temperature and hole size, as well as the source of the mixing water.
Of those things, temperature is probably the hardest single factor to get, and yet it affects the cement the most.
48 hours prior to cementing, a pilot test is conducted of the blended cement and mixed water. This testing is done to be sure that no free water or settling will occur in the slurry. Properties such as pumping time, fluid loss, time to 50 psi strength, and 24-hour strength are determined. The required pumping time is calculated and checked against a design time in order to be sure that, given problems, the cement will remain pumpable for about 2 hours beyond the expected pump time. We arrive on location at about 6 a.m. Drilling has reached TD, and 10 hours of logging is already underway.
Many different kinds of logs can be run to supply all sorts of data. Logging generally provides the information used to determine if a well is viable and if casing will be run. Logging also indicates which zone or zones are best to complete. A caliper log provides data essential to cementing. The company engineer adds up tick marks recorded on the log. Tick marks indicate annular volume, the difference between the volume of the empty hole and the volume of the casing, which the log has calculated based on the size of the casing being used. Small tick marks represent 10 cubic feet of annular volume. Larger ones, 100 cubic feet. Multiplying, the engineer easily determines the open hole annular volume. Since the cement is to extend part way up into previously cemented casing strings, he also calculates that annular volume, using capacity and displacement tables, and adds the result to get an estimated total required cement volume. Then he compares this estimated volume to the volume calculated from published displacement tables. He does this in order to reduce the likelihood of significant error. Based on experience in this particular field, the engineer adds 35% excess cement to the estimated volume in order to guarantee the desired fill-up. Suggested excess volume may range from 10% to 100%, depending on the area. While the well is being logged, the float valve, centralizers, agitators, and Texas pattern shoe are inspected. Earlier, with the casing on the pipe rack, the shoe was welded in place and the agitators were installed with Allen screws. The engineer now marks individual casing collars so that the casing crew can easily identify where a centralizer needs to be installed. The spacing of all well equipment is usually discussed in advance with the tool pusher. In this case, yellow markings show that centralizers will be needed on every other joint of casing throughout the pay zone, as well as 120 feet above the pay. With the logging complete, the first joint of pipe with the Texas pattern guide shoe at the bottom is raised into the derrick. The shoe enters the well bore. The joint is run in the hole, and the slips are set. A second joint is raised into position. The thread protector is discarded, and the joint is left to hang while the automatic float valve is installed in the casing collar on the first joint. The pipes are then assembled with power tongs, and a centralizer is positioned over the yellow marking on the collar. A worker hammers in pins to hold the centralizer closed. The string is raised, and the pipe with the first set of agitators is run in the hole. This process will be repeated over and over again during the next few hours until all the pipe is in the well. The cementing company arrives on location while the casing is being run. The company engineer reviews the job thoroughly with a service company rep to be sure that all the materials and equipment previously agreed upon are on location. They review the call sheet, the bulk plant load sheet, and make notations on the wellbore diagram. The service company rep then supervises the positioning and rig-up of equipment. The pump truck is positioned with the most direct line possible to both the 500-barrel mixed water source and the rig floor. The lead cement transport and the tail cement transport are positioned so that short, low-pressure lines can be easily connected to the rear sections of all trucks. The crew first assembles the flexible low-pressure line between the pump truck and the mixed water tank. They clean the threads and mating surfaces with a wire brush, join sections together, and hammer the unions tight. Mixed water will be drawn through this line by a centrifugal pump on the truck and delivered to a mixing manifold on the recirculating mixer. Up on the control station on the pump truck, the pump operator can divert the mixed water from the mixing manifold to either the displacement tanks or the recirculating mixer. Once the job begins, the pump operator will control the entire operation from the control station, monitoring pressures and rates at the instrument panel. Next, the crew assembles the steel high-pressure line that will send cement slurry from the pump truck to the cementing head. Again, they clean, lubricate, and hammer the unions tight. When the line has been assembled as far as from the pump truck up to the rig floor, the lead cement transport with its appropriate identifying tag is backed into place. The crew runs a flexible low-pressure line to connect the transport with the pump truck. Then the tail cement transport backs into place, and the crew installs another low-pressure line from this truck to the pump truck. As soon as all the casing is run, the cementing head is attached to the collar at the top of the last joint of pipe. This single-plug cementing head contains a solid wiper plug that was installed back at the service company's yard. There, a worker connected a copper wire securely fastened to the wiper plug to another copper wire that protruded out through a sealed and lubricated hole in the quick change cap. He then pushed the wiper plug into the cementing head and installed the cap. When the copper wire disappears from sight during the job, it will signal to everyone that the plug has been released into the casing. The service company then completes the high-pressure line by installing a multi-jointed steel hose that connects to the cementing head. Such flexibility is required to enable reciprocation of the casing string. The casing crew then begins to circulate fluids and reciprocate the pipe.
Pipe movement, either reciprocation or rotation, should be carried out all the time that you're conditioning the well, conditioning your drilling fluid before the cement job. Continue through the pumping of cement as long as you're moving fluids in the well bore until you bump the plug, and then it should stop. Post-plug reciprocation or rotation is not recommended because the debris that you remove is not swept from the well.
The well is circulated for 30 minutes, and the pipe is continuously moved up and down about 10 to 20 feet. At the end of this time, a pre-flush fluid is pumped into the well to condition the hole. The pre-flush serves to thin the mud, scour the wellbore, and increase wellbore fluid viscosity.
The effective volume of pre-flush is generally determined with a 10-minute resident time. By that we mean it needs to pass the same zone for 10 consecutive minutes in order to do a good job of cleaning the pipe and formation.
Or some predetermined amount of fill, such as 2,000 feet in the annulus, or some predetermined volume, such as 500 or 1,000 cubic feet. Particular experience or experience in a particular area determines pre-flush volumes to a large extent.
Moments later, the operator is sending the lead cement slurry into the hole, immediately behind the pre-flush. This cement is designed with less density than the tail cement, so that it will exert minimal hydrostatic pressure on the lower zones. The slurry mixing and pumping process will continue for about 45 minutes. Pressurized air forces dry bulk cement out of the bins on the lead cement transport, through the discharge line, and up into a surge tank on the mixer at the rear of the pump truck. In this recirculating mixer design, the surge tank, actually a holding tank for the dry bulk cement, portions cement through a valve that empties into a mixing module. There, mix water and bulk cement quickly combine and then discharge into a recirculating tub. A centrifugal pump sends the slurry through a densimeter behind the tub, and then recirculates the slurry either back into the mixing module, where water or bulk cement can be added, or back into the tub. Once the slurry has reached the correct density, it is drawn from the tub into the triplex pumps. The triplex pumps, powered by diesel engines rated at over 300 horsepower, discharge slurry into the high-pressure line that leads up to the cementing head. The pump operator tries to maintain a pump rate great enough to place the cement in turbulent flow. If turbulent flow could not be achieved due to pressure or rate limitations, the operator would pump at the maximum rate possible.
Okay, the question of mud removal and displacement rates has been undergoing quite a bit of change recently. Traditionally, the feeling was that you tried to attain turbulent flow. We do not feel that turbulent flow can be obtained at reasonable pump rates with a cement that's well designed from fluid loss and free water control viewpoints. Recent research by several of the service companies has led to what might be called the maximum energy displacement theory. In other words, it's not the flow regime in the annulus per se, it's the amount of energy that you're putting into removing the mud from that wide side or that narrow side. So in general, the more energy you can put into the well, the better off you are. The drawback is in many instances, if you pump too fast, your equivalent circulating density is high enough that you can break the well down. So in essence, pumping fast isn't the only answer. You have to tailor your displacement rates to the particular well conditions.
Throughout the job, the service company collects slurry samples and checks the density with a pressurized mud balance. Often, other wet samples are collected and observed for free water and set, although surface setting time is usually different from downhole setting time. Most importantly, the service company also collects dry samples of bulk cement during the first, middle, and last stages of both the lead and tail cementing. The samples being taken here will be stored at the bulk cement plant and can be laboratory tested if problems arise. Sometimes oil companies choose to maintain their own dry cement samples as well as samples of specific additives as supplied by the various service companies. As soon